Okay, this is Thursday's lecture. And the purpose of this lecture is to try to figure out what's going on with these inverse functions. Problems like this: what is the sign of the sine inverse of 3 or 0.37? Or what is the sine inverse of the sine of negative pi over 7? A couple with sines or a couple with cosines. What is the cosine of the arc cosine of negative 5/8? And what is the arc cosine of the cosine of, and let's do 5 pi over 3. Okay. And if we look at these as inverse functions, and you see that this one really has an answer of 0.37, and this one has an answer of negative pi over 7, and this one has an answer of negative 5/8. Now, none of these are calculator problems, by the way, but this one is not equal to 5 pi over 3. And in fact, if we had to figure out what it was equal to, it would have to be equal to pi over 3. And so the first question is, what's going on here? Why is it that sometimes functions and their inverses undo each other, right? The inverse and the function, they undo each other, but sometimes they don't. So here they don't undo each other. You don't get 5 pi over 3. You only get pi over 3. So let's back up a little bit away from trig just for a sec and look at some other inverses that we know. Suppose we had the cubing function and we had its inverse, which happens to be the cube root function. And we were to look at a graph of these two functions. So let's do this one in red so that we can see the graphs differently. F inverse is the cube root of x. Okay, so the cubing function, you know, passes through the origin and rises like that. Okay, and the cube root function also passes through the origin, but it passes through vertically and goes like that. And by the way, if we were to draw in the line y equals x, that would be this line right here. Remember, their graphs are images of each other about the line y equals x, because when we find inverses, we swap x and y. Okay, but just ignoring that for a sec, could you talk about the domain of each of these? So the domain of the y equals x cubed function is all reals, and the domain of the cube root function is also all reals. Now, as a consequence of that, we can say that if we take any number and find the cube root, any number whatsoever, and then cube that result, we will always get that number back every time. Or we can also say that we could take any number and cube it, and then take the cube root of that, and we will still get that number x. If I'm using my f and f inverse notation, okay, so this first one, the inside function, this cube root function, that was the one I did by red up there on the right. And then the outside function is the f function in blue. So this is saying f of f inverse of x will be equal to x all the time. And the second one, I'm doing the square or the cubing function first. So this is saying f of x, and then on the outside, I'm taking the cube root. So f inverse of f of x will be x all the time. Okay? So Yeah, maybe I just move these out of the way. There. So that's one of the results of having the domain being all reals. Okay, another example of a function and its inverses. Now we're going to get to the trig stuff in just a minute, but I want to go back and talk about some stuff that you should already know, like cube roots and cubing. So let's look at another pair of functions that are inverses. So f of x is e to the x, and the inverse of that, f inverse, is the natural log of x. And if we draw graphs of these, just like we did before, you would note that the exponential grows like this, right? And the logarithmic grows like this. And if we were to put in the line y equals x, just as we did before, we would see that they are mirror images of each other. And we have all these, mirror image points. This is the ordered pair 0, 1. There's an ordered pair up here, which is 1e. And likewise, on the log graph, there's the point 1, 0, and another point, which is e1. So these are symmetric points about this line y equals x, okay, or inverse points if you want. It's even true about the asymptotes. The blue one gets really, really close to y is equal to 0, and the red one gets really, really close to x is equal to 0, right? We're swapping x's and y's. Okay, so that's nice to know, but let's look at the domain, because that's sort of what I'm most interested in here. The domain of the exponential function is all reals. I hope you could agree with that. So domain, all reals. And the domain of the log function, now this one is different. This is only the positive reals. Right, x has got to be bigger than 0. That's the only numbers that you're allowed to say. Maybe we can do it in interval notation. It's the interval from 0 to infinity, right? Only the positive reals. Okay, now how does that play out when it comes to this idea? Because what we're going to be investigating is f of f inverse of x. What does that equal? Or f inverse of f of x. What does that equal? Sometimes this will equal x and sometimes it won't. And it has to do with the domain. Okay, so we called f our exponential. So let's look at this one first. Suppose I had f inverse of f of x. Okay, so what's going on there? So let's see, the innermost function is e to the x, and the f inverse function was the natural log. So what is the natural log of e to the x? What do we get out of this function? So before I answer that, I have to ask, what is allowed to go in there? Can I put in positive numbers for x? Well, let's look at the domain. The domain of e to the x was, in fact, all reals. Right? So yes, we can put positive numbers in for x. We can put negative numbers. This is any x is allowed. Okay? And if that's the case, then we're going to come out with that x. That's perfectly okay. And it's probably not a bad idea just to, grab the calculator just for a minute. Let me put in, let's see, y is equal to e to the x. Right, y1, and y2 is the natural log of x. So what I'm doing now, I'm doing y2 of y1 of x, like this. Right, so the y2 is the log and the y1 is the exponential. So let me go to my home screen and try doing that. To get y2, I go to vars, and then yvars, select function, and select y2. So that's the y2, that's the red over here. I've just done this. Now I do have to open up a set of parentheses. Okay, so now I've got y2 of, and now I'm going to be putting y1 in. So go back to vars, and then yvars, and then function, and this time select y1. So now I've got that, and then I can put a number in for x, and I can put in any number, right? So any x is allowed to go in there. So let me just try 10, and then when I say, please evaluate that, Mr. Calculator, it comes back 10. I can put in negative numbers. Now, you should be able to recall this. So second enter, that recalls, and then let me arrow over and change that to a negative 10. And once again, I get negative 10. So the log and the exponential are inverse functions. Now, suppose I wanted to do the other one. Suppose I wanted to do f of f inverse of x. So now I'm going to be dealing with this idea right here, okay? Or if I'm doing it in terms of logs and exponents, I'm going to be doing e raised to the natural log of x power, right? So what is this going to be equal to? Do we get x out of it? And before we answer that question, we have to look at the domain right here. What is allowed to put in for x? What is the domain of x? Question mark. Well, as we said before, the domain is only positive numbers. That's the only thing that we are allowed to put in to the log function. So if I said, what is e to the natural log of 10, that should work out to be 10. But if I said, what is e to the natural log of -7, this is bogus. This is not going to work. So maybe we can try that back on our calculator again, just to verify what's going to go on. Okay, so once again, the y1 is the exponential, right? And y2 is the log. So this particular construction, I'm going to do y1 of y2 of 10. Okay, so this is the e raised to the natural log of 10 power. So let's see how that works. Go back and vars, y vars function y1, and then we're going to be putting in vars, y vars function y2, and we'll just put in 10. Okay, and no problem, we get 10 out. What did I put in? Let me see where it says go to my error. Natural log of x, we're okay there. Second quit. Oh, I forgot parentheses. So whenever you get an error, go to the error. I just wasn't looking at my screen on the smartboard here. So let's try this again. Vars, y vars function y1, parent, vars, y vars function y2, and then parent, and I'm putting in 10. Okay, so that's this expression right here that we're trying to evaluate, and everything works fine. We get 10. However, if we try putting in a negative number, so second enter, and let's arrow over and edit this to maybe -5, now we're going to have a problem, right? Because what we're trying to do, look at the inner part there, we're trying to find, this is a -5. We're trying to find the log of a -5, and we're not allowed to do that, right? The log function does not allow negative numbers. Look at the graph again. Here's the graph of the log function. X cannot be negative. So we're asking over here, here's -5. It doesn't fit. So if you try this on the calculator, I hit enter, and it says, sorry, you can't do that. And then I'll say, okay, well, go to where's my problem? And it shows up at that log. I'm trying to put a number in for the log, and I can't do that with a -5. Okay? So let me sort of wrap this up with logs and exponentials. We can say that the natural log of e to the x will always equal x every time. And we can say e to the natural log of x will equal x if x is bigger than 0. And if x is not bigger than 0, then this is going to be undefined. So maybe we can say that as well. E to the natural log of x is undefined undefined, if x is less than or equal to 0. Okay? Now, with those two as background, we can look at our trig functions. So let's do the sign first. We know what f of x is the sine of x looks like, and we're going to be looking at its inverse function, f inverse of x, which is called the sine inverse of x, right? So let's see, when we drew a picture of this, we noted at the very, very beginning of what we were doing, we had this wave, and we said we cannot find the inverse of that because it's not invertible. It is not one-to-one. And we had to restrict the domain, so we only looked at that part of the wave. Right? That was the only part of the wave we considered, and we got rid of all the other bits of the wave. Now, this is sort of a boring picture, but that's how that sine inverse function was created. You noted that in the domain here, we said, now remember the x here is the angle, this is x, this is y. So the domain, we had all the x's from negative pi over 2 up to pi over 2, and that corresponded to this point right here. This is pi over 2, and this point over here was negative pi over 2. Okay, when we drew the graph of the sine inverse, and you're not expected to do this one on Monday, except for maybe as a bonus or something, we had a picture that looked like this. It went through the origin and went up to a point there, and a point there, and this was up at pi over 2, and this is down here at negative pi over 2. But the domain here was from negative 1 to 1. Okay, so the domain over here, negative 1 to 1. So I mean, if you just think about, if I have a problem like what is y is the arc sine of x, the only numbers I can put into that, this x value has to be in the domain negative 1 to 1. It would make sense to say, tell me the arc that has the sine of, what did I have up here? I had 0.37. Tell me the domain of, or tell me the arc that has a sine of 0.37. That certainly makes sense to do. Okay. On the other hand, if I said, tell me the arc that has a sine of 1.37, this is impossible, right? You can't do that. There is no arc or angle that has a sine of 1.37, so this is not allowed. Okay, now let's look at some problems. If I had, and again, maybe we can go back and look at these guys. So these blue ones here, what is the sine of the sine inverse of 0.37? Okay, so what is the sine of the sine inverse of 0.37? Okay, the first thing we note is that if I'm asking for the sine of the sine inverse of x, I have to make sure that whatever x's I put in here are legitimate. So I need the domain of that sine inverse, and here it is. I have to have an x between negative 1 and 1, and 0.37 is certainly in between negative 1 and 1. So that says as long as I'm in that domain, I can just write the answer down, 0.37. And, you know, we could check that on the calculator. I don't need to do y1 and y2. I can just do what is the sine of the sine inverse of 0.37. Okay, and we get exactly the same thing out again. On the other hand, if I put in a number that's not between negative 1 and 1, suppose I say, what is the sine of the sine inverse of 1.37? I should suspect now that this is going to cause problems, right? So let's see, what is the sine of the sine inverse of 1.37? And I hit enter, and it says, sorry, you can't do that. This is not allowed. This number is not in the domain of the sine inverse function. So this is undefined, undefined. Okay. Now, let's flip it around the other way and we'll do the sine inverse first. Okay, so what is the sine inverse of the sine of x? So this is sort of like what we're trying to get a handle on. And to do this, we have to first of all look at the domain of the sine of x. Now, if we're dealing with this arc sine, remember we had a restricted domain. The full sine wave, you could put any number in because the full sine wave had a domain of all reals. But now we're only considering these values. So pick a number between negative pi over 2 and positive pi over 2. Oh, I don't know. Let's see. This is going to be about, this is 1.57 thereabouts, and this is about negative 1.57. So I'll pick some number in between, like, I don't know, 0.82. So if I said, what is the sine inverse of the sine of 0.82? I would look at this and go, okay, this is a legitimate number to pick. That number is in that domain. So I would suspect the answer would be 0.82. And in fact, it works out fine. So if I said, what is the sine inverse of the sine of 0.82, it's going to come back and say 0.82. And you'll notice I don't need a calculator to do this. I'm going to know that works all the time anyway. If I put in an arc or an angle in radians, so let's see, I need an arc or an angle that's between negative pi over 2 and positive pi over 2. How about pi over 7? Certainly the number pi over 7, a seventh of a pi, is between negative pi over 2 and positive pi over 2. So that's legitimate. I will know without my calculator that this works out to be pi over 7. You can try it on the calculator. It's not going to be quite as satisfying because the calculator doesn't print out pi over 7. This is what I'm trying to do. Sine inverse of the sine of pi divided by 7. And I end up with this number. And, you know, so it doesn't, but in fact, it is pi over 7. If you just check, oh, what is number pi over 7, Mr. Calculator? It works out to be exactly that same number. So this would be a typical problem that you could do on the test, right? That is not a calculator problem. Just sit there and go, yes, that pi over 7 is correct. It's in this interval, right? So I know that the sine inverse of the sine of pi over 7 will be pi over 7. On the other hand, if I pick a number outside of that interval, pi over 7, okay, this is not going to be 5 pi over 7, not 5 pi over 7. And the reason I know that right off the bat is because this 5 pi over 7 does not fall in that interval. Right? Half a pi would be like 3.5 pi's over 7. This is 5 pi's over 7, which is more than a half of a pi. So if I tried this on the calculator and I said, Mr. Calculator, what is the sine inverse of the sine of 5 pi over 7, it's going to come back with a number. I'm not surprised about that. Oops. What doesn't it like? Go to my error. Oh, 5 pi over 7, Joe. Yeah, that go to symbol is always useful. If you get an error, just go to the error and see where the problem was. Okay, sine inverse of the sine of 5 pi over 7. Here's my number, but that is not 5 pi over 7. So let's see. 5 pi divided by 7 is this number, and those are different numbers. Okay, so you might want to think about what is that number? 897597901 and so forth. Okay, so that may take a little bit of thought on how to get there. So we did these. Okay, good. Now let's just do. Let's see how much time we've got running here. We're 24 minutes in. Let me do a problem out of the textbook first. These are one of the homework problems from 7.1. We'll sort of talk about what's going on. Okay, so I'm looking at the text on page 463. 463. And here's a problem. Now, this one was not assigned, but it's sort of what we were just doing. What is the sine inverse of the sine of negative pi over 10? And you're supposed to do this without a calculator, no calculator. So let me make my calculator go away. So here's the problem. How do we evaluate that? No calculator. Well, first of all, we look at the sine function, and we remember that the sine had a restricted domain of negative pi over 2 to positive pi over 2. And we ask, is this in that interval? And the answer is yes, it is. Negative pi over 10. I mean, if I were to draw a circle, maybe that would help. I know that if I go all the way up to the top, up to here, that's 5 pi over 10. And if I go down to the bottom, that's negative 5 pi over 10. Normally, we would write that as pi over 2 and negative pi over 2. So let's see, this is 1 pi over 10, 2 pi's over 10, 3 pi's over 10, 4 pi's over 10, 5 pi's over 10. This is negative 1 pi over 10, right? Negative 2 pi over 10, negative 3, negative 4, negative 5 pi over 10. So certainly this arc, or this angle, is in that domain. So this is okay, we can do this. And without a calculator, we can say the answer has to be negative pi over 10. Done, no problem. Okay, same page, page 463. Here's a problem that has the sine inverse of the sine of 11 pi over 4, and you're supposed to figure out what that is without a calculator. Okay, so once again, we look at the input here. We know it's supposed to be between negative pi over 2 and positive pi over 2. Let me get a little circle going. And let's see, this is a positive rotation, so we are going this way. But this says 11 pi over 4. Wow, that's a long ways. This is 1 pi over 4. This is 2 pi's over 4, right? 3 pi's, this is 4 pi's over 4. If I keep going around, this would be 8 pi's over 4, right? 2 pi, I'm going to keep going. There's 9 pi over 4, 10 pi over 4, 11 pi over 4 is going to end up in the second quadrant. So first of all, is 11 pi over 4 between negative pi over 2 and positive pi over 2? The answer is no, not in the domain. Okay, so right off the bat, we know that this is not going to be equal to 11 pi over 4. If the input right here was in this domain, then we know the answer is exactly the same angle. But this one's out, so we're not going to get 11 pi over 4. But now the question is, what do we get? Okay, so now I have to think, unit circle. I have sort of figured out that as I rotate around here, I'm going to end up at this location right here, 11 pi over 4. And I should know the ordered pair there. The ordered pair is minus root 2 over 2, and then positive root 2 over 2. Okay, and so that this inner parentheses right here, this inner parentheses is simply the square root of 2 over 2. And now I'm asking, what is the sine inverse of square root of 2 over 2? And now remember the domain of sine inverse, the domain of sine inverse. For sine inverse of x, we needed to have x between negative 1 and 1. Is this number between negative 1 and 1? Yeah, it is. This is about 0.77 or 707. Okay, so it's about that. So certainly we're okay there. We should be able to find what this is. Let's see, what is it? What is the arc that has a sine of the square root of 2 over 2? And if we have our diagram here, we know, oh, it's this arc right here. This is the arc that we needed, because the ordered pair there is the square root of 2 over 2, comma, the square root of 2 over 2. So the answer here, without using our calculator, is going to be pi over 4. Pi over 4. Now, that's a difficult problem, right? It's easy to tell that the answer is not 11 pi over 4. That's the wrong answer. But trying to reason through what is the right answer requires a little bit more thought. Okay, I hope this helps. We're going to do some more of these tomorrow. Come test time, probably very few problems like this. If they are, they might be bonuses or those that separate the A pluses from the A's, right? Okay, let me stop this here. I hope you have fun practicing with your triangles. Bye-bye.